Cool. All right. So next up, the next thing that we're going to demo is to run a small Java app. Let me actually show you the source of that. It's one of our test cases, by the way. You also have access to that. It's part of the repo. And what it essentially does is it just hashes a bunch of stuff in an infinite loop. And when we launch that, then the agent should pick it up in a moment. And there we go. And you already see the Java traces rolling in. Same here. You essentially have the whole stack trace from libc through libjvm into the Java code.
So how much of this?
Go ahead.
How much of so this viewer here, this dev filer, is this like a common tool that I'm unaware of, or is this like a custom one that you guys have written? This
It's an
visualizing.
internal one right now, but we intend to
Okay.
open source it eventually. It's like we don't
What
have an ETA. Yeah. Go ahead.
is there? First of all, really cool. I love this thing. Second, is there any significance to the colors you have here? Because I noticed there's another color that's popped up. The AES. Like you have like the teal, you have like the offset green, you have the purple.
Yeah, I'm really bad with naming colors, but like this bluish thing that is native frames, like the purple thing is kernels, and green is Java. Essentially, every language has their own thing. Yeah, we could also do Ruby, etc., but I think it's not in the interest of time. We're probably not going to be like you saw the concept, and it's going to be the same for all the other languages that we support. Yeah, essentially, you saw the flame graph. Here's a few more, like the functions view, etc. You have a heat map. You can zoom in, blah blah blah. For the purpose of this demo, I think that is all I'm going to bore you with, and then let's get to the code review, I suppose. Unless there's any more things you want to see, there's a good point to ask us now, because I'm going to close it now.
I'm all good, thank you.
All right.
Looks cool.
Let me fix the view here. Okay. Walkthrough-wise, we start with the user mod components. Essentially, we have two portions in the agent. One's the user mod portions. It's all written in Go. And then we have the kernel mod portions that are all written in eBPF-C. The central one pretty much in the host agent is the tracer. The tracer is like if the host agent has one thing that is essentially a main type, that is it. It's instantiated in main. It sets up all the BPF maps, loads the unwinders, and instantiates the process manager. We get to that on the next slide. And it also serves as the central event pump, essentially, like all the BPF events, all the ring buffers, etc., that we have with the BPF code that is pumped through the tracer. It also creates a bunch of timers for everything that is poll-based, and essentially is the heartbeat for all the components that live below it. The process manager is, like mentioned previously, it's instantiated by the tracer. It keeps track of all the processes running on the system. Essentially, it will, like when it is asked by the tracer by a timer, it will go to /proc and look through all the processes that we have, update the list, essentially create like a diff of processes that have exited, processes that have been newly spawned, and then it will go through all the it will create events for that and report that downstream. We'll get to the consumers these events later, and it also keeps track of the mappings within these processes. So mappings in that sense is the executables usually. So if there's a new executable loaded, that is detected and it is reported as an event to the interpreter handlers that we will get to later. Yeah, I almost forgot. The process manager also manages the executable info manager. That one is responsible for essentially everything that is per executable. So you might have executables like libjvm that are loaded into hundreds of processes. If you have, for example, a Kubernetes cluster, So it would be wasteful to do everything per process. Instead, we have this this manager that deals with per executable stuff, and yeah, executables are uniquely identified via a file ID that we have pretty much arbitrarily defined as something that is both efficient and works. Like in our experience, it has been working very well to actually determine that things are unique. What we're doing there is to take the first page of the executable, concatenate it with the last page of the executable and the length of the executable, and then we can send that through a share hash function. One might be asking why not hash the whole executable, and like it becomes rather obvious the moment that you look at libclang, for example, or similar executables that are multiple gigabytes. So yeah, you kind of need a hash function that you can execute faster in order to not consume too much cycles. Yeah. Once a new executable is detected, then the host agent will ask the stack delta manager to create or load from disk cached stack delta mappings for the executable. We need those stack delta mappings to unwind native code. Native code usually, like you probably all know, native code usually doesn't come with stack pointers unless you're like there's a shift back towards it. But right now, the situation is that most distros don't ship stack pointer enabled. So what you need to do is you need a separate source in order to be able to unwind the stacks to get the deltas that you have to add to the stack pointers in order to unwind the next frame, I guess. What we are doing there is we are extracting that from EH frame or Go PCLN depending on whether it's Go or any other language. EH frame is actually intended for C++ unwinding. I see a hand raised there.
Hey, yes, out of curiosity, what happens if there are two executables of from the same file showing up in is it like a problem with the collision there or something? Like, can you like dereference by process ID or something? Or like if you have, given that it's like identified by the file ID, is there a possibility to have two at the same time? And if so, what happens?
So everything that the executable info manager deals with is per executable. So if the same executable is mapped into 3 processes, it doesn't matter because all the information that we extract there is per executable, and it would translate to other processes as well. If there is stuff that is, for example, has memory addresses that are particular to another process, to a single process, then it wouldn't be stored in executable info manager, but in process manager. And in process manager, everything is per PID, so there's no problem with that.
Yeah, so it's kind of like a namespace or a scope down, essentially. So that's why you can't have the collision here. But okay, appreciate it. Thank you.
Good, right. So once we have the data extracted from the EH frame or Go tables, I was just explaining that, I guess. Yeah, so EH frame is the C++ unwinding info. It's actually originally it was meant for C++ exceptions that need to unwind stack. But it turns out that you can also use this information quite well to unwind stacks for profiling, and that's what we're doing. Go PCLN is Go's internal data structure for storing but pretty much all the runtime information. It also happens to contain enough information to unwind stacks with, because Go also uses that to create its own stack traces. Once we have the deltas, we persist them on disk, so you don't actually have to re-extract them every time. And yeah, that is loaded the next time that we see the same executable. The last thing that the executable info manager does is it asks all our high-level language unwinders whether they detect the executable as some sort of interpreter. For example, libjvm, libpython, etc. We detect these, and everything that we can extract that is per executable will be extracted at this stage. So let's say for Python, we need to extract some struct offsets, then we would go ahead and start disassembling Python in order to extract these struct offsets, etc., and cache this information for every Python interpreter that comes up after that, so we don't have to redo the work. Yeah, next is interpreter. That is a pretty large directory, I suppose, and also a package. It has a lot of sub-packages. It's the top level package is essentially defines the interfaces and types that all the high-level language interpreters implement. It's I would say it's probably the most important part of the whole product, and that's pretty much where the magic is at. The first main type in there is the interpreter.loader function pointer definition, I suppose. It's the thing that the executable info manager uses to pass in first a handle to all the eBPF maps that we have. There's a separate type that has essentially, it's a handle to all the eBPF maps that we have. And the second one, the loader info, is a bundle of information about the executable. And like honestly, I forgot the details, but the important part is there is the executable in there that you can analyze with that. Then the loader, there's a list of interpreters globally somewhere where all the loader functions are listed, and then executable info manager will just loop through that and ask every interpreter, do you want to handle this executable? And if someone says yes, then it's going to be cached. Oh yeah, I forgot. What it returns is the interpreter.data interface, which is what we have on the next slide here. So the data interface is so simple it could basically also be a function pointer. It just has the attach method. That is what is stored in the executable info manager per executable. And the process manager then uses this interface to actually create concrete instances for that, for each process that has this interpreter loaded. What the implementations usually store in these concrete implementations of this interface is disassembled, like they disassemble the interpreters in order to determine struct offsets. Everything that can be done with static analysis that we need is going to be stored here. Yeah, and once attach has been called with the arguments here, it returns an interpreter.instance, which leads us to the next slide. This, as you can see, has a few more functions. It is the per process interface. This is going to be instead for every single process that has this interpreter loaded, there's going to be an instance of that. And it is responsible for maintaining all the per process maps that we have, that essentially it's supporting the BPF code and provides it with all the information that it needs to unwind the code for this particular interpreter. In case of, for example, Python, that's not going to be a lot of information. That might be a few struct offsets that have been statically determined. Usually there's not much dynamically wise, but in terms of with languages like Java, there's going to be a lot of stuff in there. There's like locations of where the heaps are, where JIT functions are, JIT regions, subroutines, where they're located. And all of this is essentially like it periodically receives updates about mappings that have been created, that have gone away, and where it has chance to update these mappings and always have an up-to-date map of, always provides BPF with an up-to-date state of the process so that we can unwind without doing a lot of work. We will want to make the kernel path fast. And that is essentially what provides that. And the second important purpose of this interface is symbolization. A lot of symbolization cannot reasonably be done in BPF, at least with the kernel versions that we are supporting and the restrictions that come with that. So the BPF tracers actually do minimal work. They extract pretty much just, for example, bytecode offsets or something like that, send that to user mode, and user mode then goes ahead and reads the actual symbols from the Java process, for example. Yeah, that's about it. The trace processor is something that lives beside the tracer. Essentially, it's another top-level component. It's hooked up to the tracer and receives the raw traces that come in from BPF. And the purpose is to enrich them and to transform them into the final format that we eventually send out to network. It does that by adding in the container and pod info. It caches trace symbolization. So for example, if we see the same trace, we have seen it before, then we don't have to do all the memory reading again. We can avoid that and instead just use the cached values. If values have not been cached before, then it will go to the process manager, which will in turn go to the interpreter handlers to actually do the symbolization of the frames. The completed frame, once it is done, is then forwarded to the reporter. The reporter is the last component that we will look at here. And it's in the repository, if you look at it right now, it's just bare bones because it used to implement our proprietary protocol. But we threw that out, and the intention is to instead have it implement the outer protocol. In there it has a public interface that defines a bunch of methods for sending out various information that we have collected. Most importantly, it's going to be traces and various metadata. The information that is being sent is enqueued in FIFOs. If there is some kind of back pressure, the collector cannot respond in time, it's just going to fall out of FIFO. Essentially, it's intentionally lossy, so we never block or essentially leak memory or something like that. We rather drop them than doing that. The reporter, when it is created, initially sets up a gRPC connection to the collector, and on a timer, I think the timer was a timer of 5 seconds. I think every 5 seconds it will flush the FIFOs out to gRPC, and yeah, like I mentioned previously, in Elastic that implements our state for custom stateful proto, and in the future we intend to make that implement the stateless proto that we just merged recently. Any questions so far? Nope. In that case, I will just continue. Let's get to the kernel portion then. I'm starting to get the impression that my 30 minutes might not be sufficient, but let's see.
Don't worry too much about that, Joel. Like, this is very, very useful.
Yeah, I say
Cool,
go.
cool. All right. Kernel portion, probably what everyone waited for. At least that would be what would probably excite me most. It's all the good BPF code. Let's start with the minimum kernel versions that we support, because they define the restrictions that we have to work with. People like LTS kernels, so that's what we support. We try to support the oldest kernel that we reasonably can without making profiling impossible, I suppose. For x86, that is 4.19. I think, like, I haven't joined the company by the point that this was decided, so it's a pretty old kernel at this point, and yeah, but we're still supporting it. For ARM, it's a bit higher. The version is a bit higher because it turns out that there is a breaking kernel bug for ARM64 kernels where it's impossible to read user mode memory from BPF in any version earlier than 5.4. And yeah, it's impossible to do unwinding if you can't read user mode memory. There might be Linux distributions where patches for this have been backported, but yeah, we don't want to deal with that. So I think it's very few people that use older kernels on ARM64 because it's an architecture that has only seen wide adoption relatively recently. So yeah, that's about it. On the limitations, when working with BPF, I think it's most important to understand the limitations first that you're working with. In a way, it's quite different from a lot of other environments that you might have worked with because there are no loops. That is probably the most important limitations. There are, on newer kernel versions, there are some sort of bounded loops that you can do, but given the kernel versions that we wish to support, for us, there is no loops. And if you want to do a loop, you have to do pragma unroll, which is essentially it tells the compiler to just paste the same loop 10 times behind each other instead of actually looping, because you can't do backward links, backward jumps in BPF assembly. So in addition to that, we have a limitation of 4K instructions per BPF program that, combined with the loop limitation, makes this for a bit of code golfing. Because yeah, you can't get over the 4K instructions, otherwise the verifier will just refuse to load your program on older kernels. 4K instructions would be prohibitive. We couldn't do profiling with that realistically, but fortunately for us, there are tail calls. So every BPF program can issue a tail call and call into another BPF program. And thanks to that, we have a limitation of 32 tail calls that we can do in total for every invocation. and that leads us to a maximum of 130K instructions about that we can execute. And that is very much enough to unwind stack. We could probably get away with half of it.
And because this is BPF assembly, it doesn't differ between ARM and AMD64, or?
Generally speaking, I think it does not, but I think it has NDNS, and that might be depending on your host system. So if you have a big NDN machine, I think you might need a different BPF blob, but realistically, I think very few people run big NDN machines these days, so it's usually not an issue. And all the code that we have is extremely architecture specific, so we're definitely not going to support big endian anytime soon.
Just curious, from our experience at Splunk on eBPF stuff, have you guys tested on in Linux flavors like CentOS or Red Hat machines where you have to have special privileges, or it was just tested in like other like a Unix Linux flavor where you didn't need to have that?
So we don't have a testing workflow that uses Red Hat Enterprise Linux, but I'm pretty sure that we had a bunch of customers that were running it and there weren't any issues. Yeah, what sort of restrictions, like, would it be additional restrictions introduced by the verifier, or what are you thinking about?
So for example, we had customers who wanted to use it in ROSA cluster, which is basically security boosted CentOS Red Hat system. And what we found out, there are special flags that needs to be switched on in order to run over there, which only customers can then do it. But like that's why, like, in the donated system that we have this like testing where we add new flavors, but I guess it's out of the scope right now. I was just curious to ask that. Yeah. So
yeah, I think there are a bunch of flags also within the kernel that you can set in order to narrow down the scope of BPF, and I think we don't need any of those. So just the minimum BPF is what we need. But if some distro introduces more restrictions that are custom, then obviously that might be a problem. But so far we haven't run into that, and I'm pretty sure that we have customers running Red Hat Linux. Yeah. So as a rule of thumb, from these limitations, we can't do loops with more than 32 iterations. Every algorithm that we implement has to be O1. It's not everything beyond that is just a no-go. That usually works out pretty fine because most interpreters are just relatively sane and also prefer O1 structures for themselves. But there are some things like symbolization that just don't fit this, where you have to follow linked lists, etc. And that everything that falls into this category, we have to offload to user mode. The native unwinder is the piece of software that will unwind C, C++, Rust, Go, etc. And it's pretty much a virtual machine. It loads for every PIT PC. That is essentially, we start unwinding by reading the register state from the stack from the process that we have interrupted. And then we do a load across multiple BPF mobs where we extract an unwinding instruction for this particular PIT PC tuple. And then we get an instruction that explains to us how do we unwind stack for this particular tuple of PIT PC. And this instruction then essentially explains to us how we have to where we have to read stack, where do we need to read the next pointer, the next stack pointer, the next where's the PC located on stack, etc. Maybe it's in the register. It's pretty much a virtual machine implemented in BPF that executes these commands, these unwinding commands. And each of these instructions then produces a frame that is appended to our frame structure. There's a per CPU map that we use in order to persist information between between tail calls, because otherwise if you do a tail call, all the stack is gone, etc. And that's where we put the frames. So each iteration will push a frame there and then update the virtual register state to essentially the state how it would be if the function were to return already, so that we can unwind the next stack going from that. The interpreter unwinders, they work a bit differently, but from the native unwinder, I suppose, but all of them work similar in that they, well, every language that you execute needs some way to keep track of what it called. So otherwise it wouldn't know where to return to. And what we do is essentially we just reverse engineer the language, the JIT, the runtime, and figure out how does this language itself keep track of stack? How does it construct its own stack frames and stack traces? And we just reverse engineer that and then re-implement it in BPF. That's pretty much the idea.
That sounds like a lot of work. Is that like how much maintenance?
I had the same question about maintenance, because I imagine like every update to like the JVM or .NET CLR or whichever, you have to probably account for that.
Yeah, it's there's definitely some upkeep, but it's less than you would think. The initial work for something that you like hotspot that is really high. I think it took multiple months of research and implementation. But once you have that, usually the runtimes don't change all that much. Yes, they add a few new fields here and there, but it's usually a matter of a day or so to fix that up when a new major comes out. And minor, we started out by locking out minor versions as well. So essentially, if there was a minor version, we would also have to check our code. But we just gave up on this. And at this point, with the minor version, we just ignore it and it just works. The interpreters just don't change things in minor versions.
But you keep like a registry more or less of like all the major, whatever like the lowest granularity you got, like, historically you can always be able to interpret that specific version of the interpreter.
Yeah, so in the user mode code, in the executable info manager, we detect the version of the interpreter, store that, and then essentially we have a large switch of that is essentially like a Gato database for struct offsets. That we use to determine the offsets that you actually need for the version. Then maybe sometimes also there's flags that, okay, if it's this newer version, then you have to read something slightly differently. But most of the conditionals are actually, they end up being in the user mode code for symbolization. That stuff tends to change more often than the actual how the stack unwinding works.
So then, do you have good like test matrices and all this, so that way you're not just like testing against the latest version you have and whatnot?
We get to that. I have a few slides for that later.
Okay, gotcha.
Yeah, so you guys pretty much already took the points that I have made. I wanted to make in the next slide. All the points we already discussed, I think. The struct offsets dumping is essentially, the struct offset is what always changes with every minor and major version. There's pretty much always going to be some structure offsets that change because some fields were deleted or moved or whatever. But at this point we have mostly automated that. It turns out that if you use GDB, there's Python support, and GDB has this nice pseudo C syntax that you can eval. So you can just do a bunch of offset offs within GDB, and then 10 seconds later you have all the offsets and zero work. So yeah, all the remaining stuff in the slide I think we already covered previously. So at this point, I figured that some people would be wondering why go through the effort if there's JIT dump and perfmap. If people are not familiar with that, those are formats that are spec'd out by, I don't know exactly who, but the specifications live in the Linux kernel tree. And both of them have the same purpose with different approaches, and they define mappings from program counters to the function name. And the idea is for Linux perf, the perf profiler, to use these in order to resolve PCs to function names. And yeah, the formats are relatively simple. In terms of in case of perfmap, it's just a literal text file with 3 columns. I think it's start address, length, and function name. And every time there's a new function generated by, for example, JVM, it's going to have to regenerate the whole file, and we're going to have to repass the whole file. I don't think I have to explain to anyone here that it's not going to be particularly efficient. JIT dump is a bit better in that it's a binary format that you can pass more efficiently, and it has append support, so you can just track the file offset and then append. But there's still a bunch of limitations that we get to next. So most importantly, I think for us personally, that was that none of them are enabled by default. So as a user, you always have to restart your VM, rebuild your containers, etc., to enable these flags. Otherwise, you can't do unwinding. Sorry, my voice is dying, I'm afraid.
Yeah, Joel, just heads up. So I want to make sure we have time for, in case people do have questions, whether it's even the low level stuff or even some high level stuff. So maybe like 5 more minutes. You think that's enough time to get through, I guess, the key pieces that you wanted to get through?
I shall try. My voice agrees with your sentiment, apparently.
Okay, let's say, yeah, like, 5, give or take some, and then we'll leave the rest of the time for questions.
Cool. So essentially, the problem with JIT dump, it doesn't have function names, doesn't have file names, line numbers. There's no support for inline functions name. The overhead is brutal in terms of .NET Core. If you enable it, Microsoft says you have 10 to 20% overhead. So yeah, that might work for your local setup, but definitely not for a continuous profile. It's completely prohibitive. Yeah, this one we already had. The formats aren't really designed for production use. In the long term, it would be quite nice to if essentially we could bring our own standard that interpreters may be able to implement. But I think I'll leave it at that and skip it in the terms in the interest of conserving time. Yeah, next up I have a little walkthrough through how traces run through the interpreter. Would I skip that? Yeah, let me skip that because I think we discussed this already quite a bit, and people can go through the slides themselves. I think they're pretty self-explanatory. Let's do testing because I think that is also something that is really important. Go unit tests. We have Go unit tests. I'll leave it at that. Everyone knows Go unit tests. They test things for individual components, but they cannot test anything that is working in BPF or related to the kernel. Then we have BPF integration tests. They are also built using the Go test framework, but you don't just Go test them, but you build them as executables, and then they test stuff like communication between kernel and BPF, between BPF and the Go code, message sending, etc. All this code that crosses the boundary between kernels and cannot be tested with regular unit tests. What we do with them is we load them into a bunch of QEMU VMs with a bunch of kernel versions that we want to test, and we ensure that it passes the verifier on all those and that the message passing, etc. works. And the Cordas test suite is pretty much it's at the heart of our testing. It's what was pretty much suggested previously is what we do there is we compile the BPF code, the BPF C code into a user mode executable. We just link it into Go via CGO. So that allows us to run it like a regular program instead of just having to into kernel. That makes you able to GDB it if you want to debug something. And then we take a core test, for example, from a lib JVM, from a JVM, a core that contains the memory of that JVM plus the thread states. And then we use this core to essentially simulate a whole process. And then we can invoke the unwinders on that and essentially have them unwind every thread in this program and create a JSON fixture based on that. And that is what we use to ensure that we don't accidentally break support for old JVM or something like that. We have, I don't know, I think it's not thousands, but I think it's like 100 or so column tests. They are quite large. That's, I think, the drawback. We can compress them. They compress pretty well, but you cannot spam them. So essentially, we have column test cases for a lot of cases that we know are problematic. You can just use GDB to bring bring interpreters into states that you know were previously problematic, take a snapshot, and then commit this as a test case. Yeah, that's about how they look like. There's just one thread here. It's there's a storage for them that I will skip that for the in interest of time. And then for every single thread, there's going to be the exact unwinding, including symbolization, and that's going to be tested in our CI. There's a CLI tool that you can use to create new tools, new test cases for them, and test old ones. And you can also GDB into the test case. It's also quite useful for fixing regressions. And yeah, right now we store the stuff in S3. In auto context, it's going to be an interesting challenge. I think we might have to find something else there. Probably like something that comes to mind would be Git LFS. We have to store relatively large files, and quite a few of those, I suppose. We will have to find a solution for that. In the code that you have access to, there's, I think, Christos committed 2 or 3 test cases as an example directly into Git, but that's obviously not going to scale, particularly with JVM test cases because they're huge. Yeah, the next thing, my 4 minutes expired, I think. So if you want to take over again, then be my guest. Otherwise, I have a few, like the one of the questions that you've asked, I've addressed here, the changes compared to the agent.
I think that's probably fine. I guess, yeah, I'll just pause there and see if anyone has any questions, or if this will answer one, then yeah, maybe we can just keep going a little bit. The reason, I guess the one thing that I wanted to do is like to also take a step. Obviously this is great. Understanding the low level stuff. There's definitely some high level stuff that we want to understand as well before we can, sort of make the next step here, which would be sort of evaluating if this is satisfying some of the sort of check boxes that you guys will be able to open source this with like reasonable certainty that we'll be able to get it officially into OTel. So I wanted to make sure we're able to like talk about that a little bit. Yeah, so what is the rest of the group think? We could keep going here, or if you guys have questions, we can switch into Q&A mode.
I mean, we can arrange a second follow-up if it helps, but I think it's important to have those conversations now.
Yeah. Let's the comparison sounds interesting.
All right, let's go for it. Go ahead.
And I suppose, Ryan, like if we run out of time, which we probably will, we could also perhaps sacrifice next week's profiling meeting just instead, or do we have other things to discuss the bigger group?
Fair. And honestly, yeah. Okay, well, let's do this. Just let's talk about what we're going to talk about, and let's just go for it. Go for
it's also just not terribly long. I think we can just do it.
Cool.
Things that we have already changed. You definitely saw that we threw out the old protocol. It's no point in keeping it. We don't want to keep it ourselves. We just we will switch to the alternate protocol. So that's gone already. We threw out the ability to configure the agent with Elastic Agent. For people that aren't familiar, Elastic Agent is pretty much a manager service for other Elastic products. And there used to be the ability to configure the agent with that, and that's already gone. That's, by the way, that's also the reason why the main function is terribly long, because a lot of the stuff that used to be in the Elastic config module has essentially just been moved into main. We have to move that out again. And yeah, that's a big plus for you. The build system has much improved. Our internal build system is not great, but I'll leave it at that. Stuff that we do intend to change before donating is to implement the auto protocol. Florian actually made great progress on that already. We already have it working. Devfiler already speaks the protocol as well. You can essentially, with the internal agent, it's already possible to use the agent with Devfiler speaking the auto protocol, and it works pretty much the same as before. And these changes need to be ported over to the open source repository. And yeah, I don't have a timeline for that. It probably depends on when Florian is back. I think he's sick right now, but yeah, I expect that to land soon. Timo wrote .NET support. That is in review on the mono repo right now. And once that landed on mono repo, we are going to also port that over to the open source one. I built correlation with traces, with auto traces. Elastic calls it APM. And that is something that we have landed that will be released, that has been released with 8.13 a few days ago. And essentially what it allows you to do is you can correlate hotel traces with profiling execution that has happened in the same time. And yeah, that is already in our agent. It has to be ported over to the open source one. We're currently using a proprietary metrics format where we just have, it's pretty much just a JSON file with IDs and definitions. And then on the wire, we just send out the ID plus a value. So it's very efficient, but it doesn't fit the OTel concept. If you have an OTel concept, OTel product, it's definitely going to want to speak the OTel metrics protocol. So yeah, that's a point that we also want to address. Currently, there's a bit of an internal debate on what we do with the host metadata. The agent essentially also extracts a bunch of information about the host, cloud instance type, and it's a few hundred fields, I think. Essentially, a bunch of data you can use to generate stuff like CO2 emission data, etc., etc. And yeah, we have to decide what we do with that and how we integrate into OTel, whether we want it, whether that is something for a different product. I don't know. Yeah, and last but not least, before my voice dies completely, there's various code cleanups and simplifications that we still want to apply. Yeah, that's it. Thank you.
Amazing, thank you. That was very thorough. I appreciate the time to share that with us. Does anyone have any questions you want to start with?
All right, if no one else will, so when we talked about testing here, having gone through all the code, for one, is all the testing code we have been referencing represented in the Git repo that was shared to us, or are there other repos that have testing involved?
No, I think you should have all the testing, but you will not have all the test cases because, like I said, they're gigabytes and you can't just commit them into Git. So we have to find a solution there.
The objects were the test cases, but the logic would still exist.
Yeah, so you also have the fixture, so the JSON files, but just not the raw blobs for the columns, I guess.
Gotcha.
Yeah, so
you have a few examples.
Only the core dumps are missing, but I added 3 core dumps just to. You can actually go in, run make test, and it will run the test with those 3 core dumps that I added. So you can actually execute the core dump test. It's just not the full set because that would be too much.
Cool. And then so for the types of testing we have there, I mean, of course we have some for accuracy, but you mentioned how performance is very important, especially in production system here. Like, is there like regression testing for performance and all that as well, or is that something that, you know, feature enhancement?
We have that internally, but we don't have this on the public repo. We have essentially a server that will once a day run a fat benchmark suite. I think it's a Foronix, the Foronix suite. And then we have apply essentially performance numbers over that and compare that.
How often would you just say the testing framework is generally stable, or is like, you know, is like, I'm sure you've seen the collector, sometimes it just goes red for a little bit longer than you want it to go to. Like, are they pretty stable to test, or do they?
Yeah, we have, they're pretty stable because they're extremely long running. I think it's 6 or 7 hours or something like that they run. So that essentially gives the long run time gives you a pretty good statistical stability in there.
It's not flaky, you're like rerunning it all the time or anything after 7 hours. Okay, good.
It's also not, it's not part of the CI, so it's something that is, because you don't want to wait 8 hours for CI. So it's something that is done daily, and then we look at this periodically and say, oh, there was a regression. What was it?
Do you think we would be porting that over as well to, you know, if this is being adopted to open source, would we be running that in similar cadence? Or
I see no reason why not. So
okay. I'll let Samir and Morgan, I'm sure you guys have a decent amount of questions too.
I actually don't have any. James was basically asking most of my questions and more. So if anyone else has questions, I'll yield that to them. But overall, my feedback is this looks really well thought out. I like everything I see.
Yeah. I think I don't have a question, just a feedback when I was trying to run this from the GitHub. So I will keep on going back to the eBPF that we donated because I was part of the team which went through this process. So one of the things that we did was like, it would be nice. I'm not saying it's a must, but like it would be nice, like if you can hook it up like with PromQL or something, a small visualizer for the tracing or stuff like that. Like, we have an example for it. Like, I mean, it's not too much of work. So somebody starting from scratch can have an idea what this thing does. Is there any plan for it? Yeah.
So for getting your hands on that locally, we have prepared, if you want to use it, we have the dev file that I demoed initially in the first few minutes. We have executables for you that you can use. And currently that's only, it's speaking, it's not actually using the code that you're using from the repo because we threw out the network code there, so it cannot send anything. So you have to use the proprietary agent that we have. It's basically the same functionality-wise. It's just it just still has the protocol. But starting, I think probably in the next few weeks, we will also have the auto protocol that will be ported over to the code base that you have access to.
Yeah.
And that file already speaks out. Not the build that we can give to you right now that I have at hand already. I prepared that. But we can give you a new build of that file and that speaks out. So that should allow you to visualize data locally. Unless
Okay,
you're
so
Windows, that's bad luck.
So the OTLP protocol is coming soon for this project, right? And that would be okay, cool. Then it's easy for anyone to hook it up with whatever they want to do. Okay.
Yeah, so let me add to that. So Florian is not here. And based on conversations last week, he's going to work on the OTLP for the agent. For now, he's going to be a pull request on his own, not merge to master, so that you guys can review that independently because we don't want to overcomplicate it. But we also understand that you need to see this data, right? So the gRPC component is going to come with the OTLP implementation in that PR, and then you can visualize it using that file. Okay.
This is exactly what we did. We were in gRPC mode, and the idea was to go into OTLP and then everything. So thank you. We'll follow up.
I'll just add to that we, on Periscope side, we also have a branch with, OTLP support. So we'll likely update that soon so that it can also, support getting data from the BPF profiler just to, to visualize it and stuff. Yeah.
Cool.
And by the way, yeah, like my feedback, everything is looking great. Well documented code. I think, speaking of those concerns about like interpreted languages, we have similar we have a similar profiler where we have to deal with the same kind of issues, and we see the same thing where we don't have to update the offsets and things like that too often. For the most part, it just works, and every once in a while we do need to kind of dive into that world. So yeah, I don't know, everything makes sense to me. Yeah, looking good. I don't really have any concerns yet.
I think the questions about that from Splunk were probably from our own misadventures with network performance monitoring by eBPF, where our architecture for it relied on like effectively had little like a huge set of quirks for like every single like Linux distribution, every single version of it, and every time even there was a minor version update, we'd have to like go add a bunch of quirks for it. This looks a lot easier and more manageable.
I think
the problem was like literally any distribution of Linux, any updated version would be like, it's not compatible. We gotta go fix it.
That was very well put. Yeah. Thank you, Morgan. Like that was really. I wanted to say that. So one thing we made a mistake about, we went for everything like C groups, port, like the cardinality explosion was just tremendous.
Yeah.
So if we went for like small slice, I think it would have been better.
This is a lot more feasible to maintain. Yeah.
Feasible. Yeah.
One of the things that we had talked about was like external dependencies is something that I think Tigran and Josh had brought up. Do you anticipate that being an issue? Like, do you, I guess, depend on anything that might be problematic that we need to replace? I know you said like obviously like S3 we have to replace with something. But yeah, I guess, are there other things like that that have come up? Sounds like no.
Yes, like well, before the meeting, I was wondering what the kind of MVP looks like, and I think James, you also like the install scripts, like Docker images, like all of that. I think you already, Joel, had a quite good slide about what you want to do before the donation, but I still think we probably need to kind of think about that list, what it takes to get the minimum CI, the minimum 0.1 out, and I don't know who's doing that work, how this can be split, and so on. So any thoughts you had there where kind of you want to involve like more than just like kind of your team?
Yeah, I think I can chime in here. Right?
Mm-hmm.
If we make the decision that this is the right thing to do and the community wants it, I think that's the first thing we need to do. And then once we make that decision, we can go towards the OSS aspect, and then folks can then contribute scripts or whatever it is. So at the moment, I guess what I'm trying to do is not to expand the scope unnecessarily. Let's keep it within the context of what we have now, make that decision. And then we can talk about installation script editor. I haven't answered that. We currently have Helm, we have Docker images that customers can run. We have deb packages, RPM packages as well that folks can use, and then just the standard binary. So we could also extend that bit, or if folks want to extend it to, other areas like CloudFormation templates, etc., we can also have all of them. But the goal is, let's not expand the scope right now. Let's keep it to what we have now and make that decision first. And then we can then increase as we get along.
All right, I think we're out of time, but Ryan, if you're okay with it, maybe we sacrifice tomorrow or next week's public profiling meeting and just review this. That might be the easiest way to schedule it.
Yeah, I think that could work. Yeah, I mean, it sounds like there's no major blockers here.
None, no. Yeah.
And honestly, like I don't know if there was like much of this conversation even that others wouldn't have been able to be part of. So I think we're getting to a place, but yeah, we can talk about it in the group and figure out what we want to do for next week.
Yeah, this looks great to all the Elastic folks. Like, thank you. This is so thorough. This is fantastic.
Yep. All right.
Thank you, Joe. Thanks for putting all the effort in. I guess in the next meeting, is that when we get like an official statement, something similar, so we can proceed to the next stage, which is
I put a bunch of check marks in there. One thing we didn't talk about is like where it'll live, but I don't think that's a blocker either.
I don't think it matters.
Yeah. I mean, yeah, let's have everybody kind of go back and discuss with the teams, but I mean, yeah,
okay.
Like we can move forward here.
So maybe in that case we keep the public profiling meeting and just discuss.
I think I would lean towards that right now.
Okay, great. Yeah, sweet.
Cool. All right. See everybody.
Okay. Yes.
Yeah.